So this recording is inspired by time that Michael Robinson and I spent at Rensselaer Polytechnic Institute in Troy, New York, and sort of a shout out to Mark Holmes and Julian Cole. Mark Holmes is still teaching at RPI, and just the kind of things that these guys were famous for. So here's Julian Cole's textbook and perturbation methods. He's written a ton of stuff, and here's Mark Holmes, same type of thing. So what the idea is behind this example is, I want to give you an example of something that's a toy problem that has a lot of those same attributes in them. Okay, so this toy problem is going to show you how non-uniform step sizes can be easily handled with sheaves, and matching in the middle for two different constraints on either sides. So for like a real boundary layer problem, you might think of like a bug on a car. Okay, this is just a picture I found. The article is actually talking about something entirely different, but I just wanted that picture. So sometimes when you're driving along, you'll notice a live bug, not a dead one, sitting on your windshield, and they're just sitting there staring at you and you're driving along. And what happens is you may be going along at, I don't know, like 70 miles an hour or something, maybe not that fast, and the bug is just sitting there, and you're like, how can that be sitting there? And it's because right on the windshield, the boundary layer has to be satisfied, so that the speed of the wind has to be like 0 right on your windshield, right? So because your windshield isn't moving. So anyway, sometimes the bugs can sit there, especially if they find a little crevice they can sit in. But really, this is just something to think about, like when you're matching two things. So like here's the car in blue and the bug in red, and you think about the speed. So the speed here is going to be, let's say, 55 miles per hour or 100 kilometers or something like that. And then the speed right here has to be 0, right? There has to be like basically no flow of air right on that boundary. But very, very close to the boundary, it's going to be like really fast. It's going to be like very, very fast. It's going to drop off extremely suddenly. So it's as if the rules that apply in this zone stop applying, but it has to be continuous. There has to be some gradual transition. I mean, that's the point we're getting at, I guess. So how do you transition between these two zones in a gradual enough way? It needs to be kind of flexible, and sheaves will give that to you. I remember in grad school, Mark Holmes saying that a lot of people who don't know how to handle boundary conditions properly will just say, okay, I'm just going to just draw something like wherever I want and say, okay, here's the transition line. It's this way on one side and it's the other way on the other side. And that's not the point. You're supposed to have a limit as you go from one side and a limit as you go from the other side. And there's a sort of a gradual transition zone. There's not just a hard break where you solve on either side of the line. It's not that kind of problem. Okay, so anyway, that's enough of that background. I'm going to tell you how I came up with the toy problem that we're going to use. So without any loss of generality, I'm going to actually go ahead and glue two things together at 0. And I'm going to go out to some side and some other side. And what I'm looking for is some kind of curve that transitions roughly at 0. But I want to make sure that x, y, and y prime are all the same so that the transition is smooth, so that this is a plausible exercise to work. Okay, so what I ended up with is I decided to, on the left side, I'm going to have x squared minus 9, and on the right side, I'm going to have minus 9 cosine of pi over x. Okay, and that gives me, of x over pi. And so that's why I have this crazy end condition over here, x is equal to pi squared over 2, because I wanted this to land on a 0. I want to set a 0 boundary condition. And I'm going to go over to -3. Again, I want there to be a 0, just for simplicity. Okay, so what I did is I said, well, what are the differential equations that would lead to that? And just sort of looking at Desmos, does it look like a fun thing to do? So I'm going to be coming in the x squared minus 9, so this part here, and then I'm going to follow up along this curve and that's what I'm going to try to solve. That's the solution I'm looking for. Okay, so keep that in your mind's eye. Okay, and so I'm just showing you right now the right side of the problem. I'm allowing everything to optimize except the endpoints. Okay, the endpoint and the one on the other side at the very end is not going to be optimizable, and I'm only going to use 2 dimensions of data, x and y. All the other cells, all the internal cells, are going to have a 3-dimensional data, x, y, and y prime, and I'm going to do on the right side, I'm actually going to have h on the right side is pi squared over 32, so that when I get to the end, I end up at pi squared over 2. All right, so I'm going to have a different h on the left. So on the right, I'm going to do the following productions. So what I'm doing here is I'm just saying, all right, I want x to be x plus h at each step, and for y, I want y to be y, the existing y, plus essentially this y prime times the step size. And this bit tells me what y prime should be, and that's what I get from my differential equation. So if I just took my solution and took the derivative, that's what I get. Of course, I lose my constant, but that's kind of the whole point. Okay, so this is just a fudge factor. If we were using a differential equation solver, we would pick some kind of constant. The reason that's 1.5 is if, like, say, if I'm on this cell, I'm telling this cell what to use as its slope. So I'm going to go like halfway to the next cell, really, to sort of grab an x value and give it for the slope. Because if I don't, based on the physics of this particular exercise, it's way off, and I wanted it to be a little better. So there you go. So that's what I'm using. Now, of course, on the very last arrow, I don't use this term. That term is dropped, and these guys are fixed over here. The x and y are fixed, and so that's why I dropped that other term, so I didn't have to mess with it. Okay, so on the opposite side, it's very similar. So if I'm going in the other direction, the very same thing applies, but I have a different step size, so I called it h2, and it's just 0.25, so that by the time I get to PL12, I'm at x equals -3. And very similarly, I have productions that get me there. Okay, and the similar thing is going on as I go outwards. I'm allowing the h itself to actually be negative, so that negative 0.25, I think I said 0.25, it's negative, so that the formulas look more standard. And so I'm just taking a step, so x's keep moving right along, the y's keep moving right along, and this again is the y prime that we just got from the differential equation. Okay, and then we go ahead and code that up. And now you see, since we have so many more cells, I'm not typing them all up. I'm using loops to create them. I think we did that in the last example. I'm losing track of how many examples we did now. Okay, but we're doing this, we're generating the loops and setting everything up, and let's go ahead and see what happens. And we get an ugly graph, but the important thing is everything is linked together as we expect. So if you have forgotten to code up something, which I did the first time, I forgot to code up the link going from P0 to PL1, and then I got this weird looking graph and I knew I did something wrong, so it was actually useful. And then I'm going to wait. I'm going to pause the video because this takes a while. These things always seem to take longer than they should. But the takeaway from that is you should use the appropriate tool for your application. But if you don't know what the tool is, or you need a rapid prototyping tool, or if the correct tool hasn't been invented yet, then sheaves can get you out of this mess. Just, everything comes with pluses and minuses. And this is not the fastest way to solve this differential equation, that's for sure. So now I'm going to just look at this and say, okay, let's look at these results. I'm going to dump them into some kind of graphical software and see how bad my results were. Okay, this is StatCrunch. It's a piece of student software. It is not very robust, but I use it all the time because it's easy for me to pull it up on my computer. Okay, so this is the x, y, and m that well, just x and y, I'm sorry, just x and y that came out of that calculation. And let's go ahead and look at how this compares to the correct solution. So this is the theoretical solution from, that is the wrong theoretical solution. Hold on a second. Okay, those are the plots I wanted to show you. This is the calculated solution, and this is the theoretical solution, and you can see they look very similar, but down in here it's a little bumpy. Right, so the transition wasn't as smooth as we had liked. Maybe we should put a finer mesh closer to where that transition occurs. But just to show you what the residuals look like, they're pretty good. And then those 2 points that looked bumpy are indeed bumpy as you would expect, because you're able to see it in context here. So that's how well the method did. It was not bad at all, in my opinion, especially for something you just kind of throw together. So yeah, I guess that's the end of that example. I'll see you on the next video. Hope you're having fun.